So in the past few classes, we've been looking at generating the derivative or the function that represents slope by using the Newton's quotient, by using a limit to get that. But you may have noticed that there seems to be a pattern, and we were kind of alluding to this pattern before as well. The change in the x squared function is represented by 2x. So we went from a power 2 to a power 1 function for the derivative. The change in the cubic function ended up being a squared function. The change, this one was a little bit harder to see, but the change in the 1 over x function ended up being a 1 over x squared. Well, if we look at the power of this, the change in the negative power negative 1 ended up being a power of negative 2. Square root becomes 1 over 2 square root, while the power 1/2 became a power negative 1/2. So there seems to be this power change of a decrease in power by 1. And this is not something you're imagining if you saw this. This is actually happening. This is actually really the case. Now, it's hard to prove this other than we have some kind of justification for it, but it's not a proof. We just kind of justified it in that changes in a quadratic or linear. We looked at that, and we see lots of examples. This seems to work. And it doesn't just seem to work, it does work. This is actually a rule. This is something we're going to call the power rule. So the part of the power rule is, as we start with a power r, we're going to end up with a power that's 1 less. Not only that, that power happens to always end up as a coefficient. So power 3 becomes coefficient 3. Power 2 becomes coefficient 2. Power negative 1 becomes a coefficient of negative 1. Power 1/2 ends up being a coefficient of 1/2. Okay, so this power also becomes a coefficient. And this doesn't just work for like whole numbers, it doesn't work just for integers. We can see it doesn't work just fractions. It works for every real number. So it doesn't matter, and this is really hard to justify, but it doesn't matter what the power is. If it's a power, polynomial power, then we can say, like, for example, the change in the power pi, that's not rational or an integer. We could say x to the power pi differentiates to pi x to the power pi minus 1. So it doesn't matter that it is an irrational number. It still works. This power rule still does work. So a couple things that we want to be aware of. We know that constant here, okay, in front, the multiplier, is not really involved in the differentiation. However, it does affect the slope. It affects the slope by a factor of c. So what we're going to do is make sure that we keep that factor of c in our derivative. So an example that we saw before was when we had 3x squared. Well, it is the same as the derivative of x squared, which was 2x, and it's 3 times bigger because it's basically a vertical stretch of 3. So, but we don't really need to worry about that as we do our differentiation or as we apply our power rule, because we just as long as we keep track of it, we're okay. So an example here is, another example is a rule is that if we have polynomial parts by plus, we can differentiate those parts separately. And one of the justifications we could give this is that, well, we are basically finding the slope of this function. This piece calculates y, this piece calculates y, and we're just adding those two y values together to get the overall height. Well, if we want to get the overall slope, well, we can just take the rise here and the rise here, and we're dividing it by the same run anyways, so we can differentiate those parts separately. Okay, so any plus or minus, we can apply the derivative or differentiate separately. The last part of this is that the constant term always differentiates to 0. We kind of showed that some examples before as well. And the reason why is because it's a vertical shift. And a vertical shift is not going to affect the slope of the graph. So if I take a parabola and I have slope at point x, well, if I take that graph and I just move it up or down, well, that doesn't really affect the slope at that particular x coordinate. Okay, so the constant value has no value when we differentiate it. The other way we can look at it is if we think of this as a separate derivative, okay, like we did here, the slope on the constant value of y equals 3, well, that's a horizontal line, and the slope of that line is 0. So that's why we can say that differentiates to 0. So there's different perspectives we can take on this. Even with those different perspectives, we still end up with the same conclusion. Okay, this plus 3 doesn't affect the derivative. It differentiates to 0.